Good morning, everyone. Welcome. The topic of my presentation today is LogicMEM, automatic profile generation for binary-only memory forensics via logic inference. My name is Zhenxiao, and I'm from UC Riverside. So memory forensics nowadays refers to a structural analysis of volatile memory bytes acquired from various devices such as PC or cloud virtual machine, smartphones, or even IoT devices. And what makes it different compared to traditional digital forensics is that we can discover or recover some artifacts or evidence that are only resident in the memory. For example, like the running process, the open file, network traffic, or even loaded kernel modules. And moreover, we can use all those memory residential artifacts to perform a further analysis, such as rootkit detection or malware detection. So this figure presents a typical process of a memory forensics. So first we capture the RAM content from the target systems. Then we analyze the memory dump and report the discovered evidence and artifacts, such as the running process. And all these artifacts are managed in some K-kernel data structures. So the very important step in this whole process is how can we bridge the semantic gap between raw bytes and the forensics artifacts. And the key to this step is a kernel profile. And a kernel profile is a map of kernel data structures, including the addresses of objects and also the offsets of the fields in those objects. We can pretty much rely on the profile to reveal memory residential information. For instance, if we want to scan the running process status, we will look up the information in the task structure. Similarly, for memory layout, we can read the MM structure. In the open file, we can look up the FF structure or other file-related data structures. Well, for traditional profile generation, they typically compile a kernel module inside the system and emit debugging symbols. Well, however, this kind of approach may fail in the following situations. So imagine when you want to do memory forensics in a Crimson postmortem, where you just acquired the memory of the device and you don't want to leave any traces in the target devices. Also for like IoT or embedded systems, the compiler toolchain or kernel headers are not always available inside the system. And also for cloud providers, when they want to make sure the virtual machines running on their platform are secure, they typically do not have the permission to log into the customer's system. Another important reason is that Linux kernel is so diverse. So it upgrades so frequently, such that every time during the upgrade, the new field may be introduced or some old fields may be deleted. And this will make the layout of the object different for among different versions. And also Linux kernel is highly configurable. So as shown in this example, there are a bunch of configurations. You can choose to enable or disable those configurations when you compile the kernel, which will result in a very different layout of those kernel objects. So that being said, we cannot reuse a symbol. We use a simple profile that works for every kernel. So we have to generate a kernel profile every time before we perform the memory forensics. Okay, so this is the overview of our proposed approach called LogicMEM. We first locate the kernel memory because all the information we care about are in kernel data structures and they are all in kernel memory. And then we try to recover the global kernel symbols from the memory. Here we adopt a signature-based approach to scan the data structures that stores all those kernel symbols and try to recover those kernel symbols from those data structures. And the third step is to find the offset of forensics required fields. And here, in this step, we use a logic inference approach. So in the following slides, I will introduce this part in detail. Okay, so the first step is the fact collector. And here it does a very simple job, which is lift raw bytes into basic facts. And here's an example. So for every value in the memory, whether it's 8 bytes aligned or 4 bytes aligned, we try to decode them and make a prediction about its type. So here we make conservative predictions, meaning that one value can have different types. For instance, like the zeros can be a non-pointer or a number. So we collect a bunch of facts based on those raw bytes, and the facts contains the offset of this value, the predicted type, and also the value itself. Then the question is, how can we define a set of logic rules that works well, good enough to find the offset of forensics required fields? Well, according to our study of Linux kernel evolution, we found that there are always invariants in those kernel data structures, meaning that some fields remain stable among kernel upgrades. So here we define the object invariants as the fields that do not have any type changes or do not have any name changes. And also there's no relative order changes between those fields, and those fields will be always present in the object definition. So in order to summarize the invariants, we studied 47 major versions of Linux source code. And here in this table, we present some numbers about the study result. So for the first 4 lines, the numbers are accumulative, meaning that, for instance, for this one, in task structure, there is a total number of 146 field additions over 47 kernel upgrades. And also there are 64 times of field deletions over 47 kernel upgrades. So compared to the total number of fields in task structure, well, the changed fields are actually minimal for each of the 1 upgrade. Another thing to notice is that the forensics required field, which refers to the fields that are required to perform some basic forensics tasks, well, those are actually only a small portion of all the fields. Like in task structure, there are only 15 fields that are required to do the the forensics task. And more importantly, among those forensics required fields, there's only 1 time that a field is changed over 47 versions. For most of the objects, those forensics required fields do not have any change. So one major takeaway from this study is that those forensics required fields have minimal changes over along the kernel evolution. So we can confidently use those invariant features of these fields to construct logic rules and let the inference engine search them in the memory bytes. Okay. So here I will use this example to illustrate how do we construct the logic rules, based on the object invariance we summarized. So as I introduced, first we have the type invariant, meaning that those fields do not have type changes over kernel upgrades. So they will always be the same type. Like for the tasks field, it always be a pointer, and for the comp field, it always be a string. And also for PID, it is an integer. Then another type of type invariant is the pointer type invariant, meaning that like for these 2 fields, the MM and active MM, they always points to a valid MM structure. Also, for the auto inference, it means that these two fields, the task is always defined before the COM field. And another type of a strict auto inference is the adjacency inference. This means these two fields always have a fixed offset. Like for the PID and TGID, it always comes one after another, and there's no other fields in between. And then is the range inference. This means, this basically means the offset of the fields is bounded by the size of the object. Another type of inference is the value inference. So this cannot be observed from the source code, but we can rely on some simple heuristics to construct some auto inference. For instance, there are two fields, arg start and arg end, in the MM structure. It points to the beginning and the end of the arguments. So, we can naturally have rules to specify that the value of arg start is less than the value of arg end. Okay. For more details about what the rules look like and how do we construct the rules, you can find it in the paper. So for the evaluation, we first evaluate LogicMEM on kernels obtained from mainstream Linux distribution. And we choose CentOS, Debian, and Ubuntu. And the kernel version ranges from 3.10 to 5.10. And we show that logic rules can achieve 100% accuracy on all those on the evaluated mainstream Linux distribution. Then we build a set of kernel by ourselves using a random configuration. So when we build the kernel with random configuration, basically every configuration in the kernel objects are randomized. So we can have very different or very diverse kernel object layouts. Even that, logic rules can still achieve 100% precision, and an average of 95% recall. Apart from that, we also do some real-world cases. We also evaluated on some real-world cases. We first evaluate LogicMEM on 6 Android kernel, which is ARM v8 architecture and 64 bits. And also we chose another 2 router firmware, which is the OpenWRT and LAID. So for those systems, the traditional approach cannot produce a profile, so there's no ground truth. So what we do is we first try to generate a profile, and when we use the profile to do some forensics, and then we compare the forensics result with the runtime information we can get from the system. And here we show some screenshots of the forensics result. For this Android kernel, you can see that our generated profile can, list all the process memory layout. Also, for this OpenWRT router image, we show that our generated profile can support the process listing of volatility. And also for this late image, we show that we can list all the loaded kernel modules using the profile we generated. To sum up, we proposed a novel approach to binary-only profile generation. And our evaluation result shows that we can achieve a high precision and recall within a reasonable efficiency. And we also showed some evaluations on the real-world cases where traditional approach fail, but we can still generate the profile that supports some basic forensics tasks. And our project is open source. Thank you very much.